All right. 4.2 day 2 is where we're at. The goal here will be the same as it was in 4.2 day 1. And this is just a recap, a very brief recap of day 1, where we were finding maximum and minimum points with quadratics, which are nice to work with because, as very often is the case with quadratics, there are nice little patterns that come up, such as this one, where if we want to find the x-coordinate of the maximum or minimum, we can find that from doing negative b over 2a, which is based off of these coefficients of the quadratic in standard form. Okay. Now what you're going to see with cubics, we don't have a nice little pattern like this, so we have to go about it much differently. Okay, we don't have a little pattern that's going to take us right to the point, so a little bit more work will be required, but it's a pretty straightforward method of finding them. Really, at the end of the day, it's an approximation. Okay, we have to be clear as to what we're looking for because most cubics have a maximum and a minimum. As you can see in the graph down here, those tails go in the opposite directions, leaving a max and a min. What we need to do is work with it in factored form, and we want to narrow down our x values that we check, and using the aid of a calculator, put together a big table where we can do some guess and check to try to figure out where the maximum or the minimum point is. For example, okay, here's a cubic. Notice the three factors: factor of x minus 2, factor of x plus 1, and a factor of x plus 3. Don't bother to change this to standard form because I don't want to switch it. The first thing I want are the zeros, and from the first factor I see there's 1 at 2. From the second factor I see there's a 0 at negative 1, and there's 1 at negative 3. Now one other thing to notice here is a, the leading coefficient is 1, which is positive, which tells me that the graph is going to take on some shape like that, with the left tail going down and the right tail going up. I'm going to zoom into my graph here and put together just a rough little sketch that's going to help me narrow down the values I should check and put into my table before I start doing the work to check those points. Okay. Again, we had a, let's just check the zeros, 2, negative 1, and negative 3. So we had a 0 right here at negative 3, another one at negative 1, and another one at 2. Okay. Now because that left tail went down, I know it'll hit this 0, and all of the zeros were just to the first power. There were no doubles, which means it's going to cross here, it's going to cross again, and then cross again at 2. Now we've practiced making sketches of polynomials like this, and this is the point where I would have said, you know, for these intervals between the zeros, check a few more points to get some more accuracy here and here. Now this sketch is just serving the purpose of telling me which values that I should check, so I don't need to do that. I don't really care about the accuracy. What this shows me is if I were looking for a maximum, I've narrowed down the points I need to check. Okay? I can see that it hits that maximum between negative 3 and negative 1. Okay, I could think about this in a sense as my domain if I were trying to find the maximum. Because what I'm going to do now is make a table and use guess and check with this cubic function. But I would know from here that the smallest possible point I should start checking would be negative 2.9. All right? And what I'm going to look for here as I go through and I check more and more points, I'm expecting, based on what I'm seeing with my sketch, is that these x values, these y values are going to start increasing as I keep checking these points. Okay? To a certain extent, or to a certain point, I should say, where then the graph hits its max and the y values are going to start to decrease again. That's how I would use this to isolate where that maximum point is. Okay, so I would just keep going, plugging in these numbers, okay, and find when does it start to go down, and that's how I'm going to isolate that maximum point. Okay, the minimum would be the same thing, except from the graph I've seen here that between -1 and 2 is where I'm going to find my minimum. So again, I have to go with this route of just guess and check, but now I would know the smallest point I should start at is -0.9, -0.8, -0.7. If you feel comfortable, you could skip a few values. Just make sure that you know that you don't skip the maximum, all right? Because what you're really trying to find is when you're checking these consecutive x values, when does it start to turn? And in the case of the minimum, where do I see, okay, in other words, at what x value when I plug it in, do I start to see that it changes direction and the graph starts to increase again? All right, a little real-life application with a piece of sheet metal. This problem would look something like this. Piece of sheet metal that's 10 by 6. And what I'm doing here is I'm going to take the corners of this piece of sheet metal and I'm going to cut them off so that I can fold up the sides and turn this into a box. Okay? The variable x is what I'm calling the amount that I'm going to cut off from each corner. Okay? I'm going to cut off a little x by x square. And at this point I don't know how much that is. That's kind of the point here, is to figure that out. What I do know is that the dimensions of this box when it's folded up would have a height of x. For the length, I've got 10 inches to work with, but I'm going to cut x off of both sides, like right there and there. Same for the width, I've got 6 inches here, but again, I'm going to cut x off of each side. Now, if I wanted to relate the amount that I cut off to volume, I would take length times width times height, which would be x times 10 minus 2x times 6 minus 2x. Okay, and again, what I can do with this function is just plug in a certain quantity for how much I'm going to cut off the corner. Okay, what the dimensions of this square would be. Let's say it was like 1 inch. I could plug in 1 for x, and what I get for a y value is going to tell me what the volume of that box would be if I cut off 1 inch. So now, the goal here is really going to be the exact same as it was before. Let's say I want to find the max volume. So I've got x in my table. And I've got v of x, which again is the volume based on the value of x. All right, just like that other example we looked at, I still want to find the zeros. The first factor tells me there's 1 at x equals 0. The second one tells me there's 1 at x equals 5. And there's another one at x equals 3. Once again, the value for a, the leading coefficient, is 1, which means this graph is going to look something like this, with the left tail going down and the right tail going up. I'm going to blow up my graph here. So what I'd have now is a 0 here, right at x equals 0, 1 at 3, and 1 at 5. That right tail is going down, all right? And again, there's no double zeros, so I know it will cross here, and cross here. Okay, again, exactly how high and how low it goes, I don't really care. All I want to see from this graph is if I'm interested in this point right here, I should look in between those two zeros. X equals 0 and x equals 3. That interval, that's where I should be looking. So if I zoom back out here and look at my table, again, as far as my domain, I kind of mentioned that earlier. I could think about this as my domain. Okay, I should be looking at the possibility of cutting off between 0 and 3 inches. That's how much of the corners I should be cutting off. I shouldn't look at any other x values because I could see from the graph that no other x values really make any sense. All right, so as far as the guess and check process, the very first point I would look at would be 0.1. And again, we would go in increments of 1/10, 0.1, 0.2, 0.3, 0.4. And again, I mean, at your own risk, you can decide to skip a few to try to be as efficient as possible. Just make sure that if you're going to skip some, like for example, on this one, you really don't need to check 0.1, 0.2, 0.3, or 0.4. Okay, the ones I've listed, it's not going to be the maximum. It's not going to happen that fast. Now, I certainly don't need to check all the points up to 3 because remember, as soon as I plug in an x value and I start to see it decrease, I can stop checking. All right, or at least I don't need to go past that x value and check more because I've really now started to isolate to the nearest tenth exactly where the maximum is. Okay, so this might be one where you say that I'm going to start at like 0.6. I'm going to start closer to 1 than 0. You can certainly approach it that way because you do want to be as efficient as possible. We have a lot of points to check, but we don't have to check, every single point going up by 1/10 from 0 to 3. That's not necessary. It's just not something that we need to do. All right. Again, you'll notice here with cubics, very different from quadratics. We don't have a nice little formula that we can just plug in some numbers and it tells us where the maximum or minimum is. A little bit more straightforward. It involves plugging in points, but really the purpose of looking at this sketch was to get this, so we can narrow down the points that we have to check, so we can do it efficiently and save time. All right, because we don't want to be working in a really inefficient manner and checking a bunch of points we don't need to. All right, in this graph, let me know that 0 to 3, that's the place to start looking. Okay, that's all for 2.4 day 2. If you have any questions, make note of those and let's talk more in class.